Introduction. Greetings, students, and welcome to today's exploration of a fascinating problem in the realm of algorithms. Our focus will be on LeetCode Problem 49, aptly titled Group Anagrams. At its core, this problem challenges us to organize a list of strings into distinct groups, where each group consists of anagrams, words formed by rearranging the letters of another. For instance, consider the words listen and silent. They exhibit this intriguing relationship of being anagrams. Here, we will receive an array of strings as input, such as eat, tea, tan, ate, nat, bat. Our task is to transform this input into a structured output, a list of lists, where each inner list contains words that are anagrams of one another. In this example, we would output eat, tea, ate, bat. Notice how eat, tea, and ate share the same letters arranged differently, while tan and nat form another group, leaving bat as an individual entity. Let us embark on this analytical journey together. A frequency array for character counting is a powerful tool that helps us track how often each character appears in a string. Imagine this array as a row of boxes, each labeled with a letter from A to Z. If we take an array of size 26, index 0 represents A, index 1 represents B, and so forth, up to index 25 for Z. When we look at a string, we can easily check how many times each character shows up by simply counting and updating the respective box in our array. This method is efficient, allowing us to find character frequencies quickly without the need for complex loops. To utilize a frequency array, we start by creating an array filled with zeros. This represents that no character has been counted yet. As we read through our string, we increment the count in the corresponding index for each character we encounter. This approach not only helps us count characters, but also lays the groundwork for solving problems, like checking if two strings are anagrams, making our solutions faster and more efficient. In this slide, we have a function called char frequency, which counts how often each character appears in a given string. First, we initialize an empty dictionary named freq. Think of this dictionary as a box where we'll store each character as a key and its count as the value. Next, we loop through each character in the string. For every character, we use the get method on our dictionary. This method checks if the character is already in the dictionary. If it is, we increase its count by 1. If it isn't, it starts counting from 0 and adds 1. Finally, the function returns the frequency dictionary, giving us a clear overview of how many times each character appears. For example, if we pass the string hello into our function, we get a result that shows H appears once, E once, L twice, and O once. This method is particularly useful for problems like grouping anagrams, where understanding character counts is essential. A list of lists, also known as a nested list, is a powerful data structure that organizes collections of items hierarchically. Think of it as a folder containing subfolders, where each folder holds related items. For example, imagine a classroom where each group of students is represented by an inner list. This structure allows us to group related data efficiently. In computer science, understanding list of lists is key because it helps manage related data in an organized way. It's essential for tasks like organizing databases or implementing algorithms that require grouping, such as clustering. When working with a list of lists, you access elements using indices. Just like accessing a book on a shelf, you first find the right shelf, our outer list, then locate the specific book, our inner list. This flexibility makes it easier to retrieve and manipulate data, which is fundamental in developing algorithms and data structures. This slide presents a function called group by key, which organizes items into lists based on a common key. Imagine you have a collection of fruits and vegetables, and you want to sort them into groups. The first step is to create an empty dictionary named grouped to store these groups. Next, we loop through each item in our collection. For each pair, we check if the key, like fruit or vegetable, already exists in our dictionary. If it doesn't, we create a new list for that key. Then we add the item's value, such as apple or carrot, to the appropriate list. Finally, we return the grouped items as a list of lists. In our example, when we input fruits and vegetables, the function produces apple, banana, carrot. This way, we can easily see which items belong together. Understanding this concept helps in organizing data efficiently in various applications. A dictionary for anagram mapping is a powerful tool for grouping words that are anagrams of each other. An anagram is created by rearranging the letters of a word. For example, listen and silent are anagrams. In this approach, we use a dictionary, which is often set up as a hash table. The keys in this dictionary represent the canonical form of the anagrams, typically by sorting the letters in alphabetical order. Each key points to a list of words that correspond to that anagram group. This method is highly efficient for categorizing and retrieving words with the same letter composition. It's especially useful in applications like word games or natural language processing, where recognizing patterns in text is key. To create this mapping, we go through a list of words, sort each one to generate its key, and then populate the dictionary. If the key already exists, we simply add the word to the list. If not, we create a new entry. This way, all anagrams are grouped together, making future retrievals quick and easy. The dictionary structure streamlines data organization and optimizes the search process, which is invaluable in algorithm design. Let's explore how we can group words that are anagrams using a dictionary in Python. The function group anagrams takes a list of words as input. First, we initialize an empty dictionary called anagram map. This will hold our lists of anagrams, where the keys will be the sorted characters of the words. Next, we loop through each word in the input list. To find the key for our dictionary, we sort the letters of the word. For example, the word bat, when sorted, becomes apt. This sorted version acts as a unique identifier for anagrams. If that key doesn't already exist in our dictionary, we create a new list for it. Then, we append the original word to the corresponding list. Finally, we return all the grouped anagrams by converting our dictionary values into a list of lists. As an example, when we run this function with the words bat, tab, eat, tea, and ate, it groups them correctly based on their anagram relationships, showcasing how effective this method is for organizing words. To solve LeetCode problem 49, group anagrams, we first need to understand what anagrams are. Anagrams are words formed by rearranging the letters of another word, like eat, tea, and ate. Now let's break down the steps to group these anagrams. First, we initialize a hash map, or dictionary, where the key will be a tuple of sorted characters from a word, and the value will be a list of words that match that key. Next, we loop through each string in our input list. For each word, we sort the characters to create our key. This key is crucial because all anagrams will yield the same sorted tuple. We then check if this key exists in our hash map. If it does, we append the original word to the corresponding list. If it doesn't, we create a new list with that word. Once we've processed all the words, we collect the values from our hash map, which are the grouped anagrams, and return this final list. This approach is efficient because using a hash map allows for quick insertions and lookups, while sorting provides a consistent way to identify anagrams. The overall time complexity is O(n)k log k, where n is the number of strings and k is the average string length. In this problem, we are tasked with grouping anagrams from a given array of strings. An anagram is formed by rearranging the letters of another word, utilizing all original letters exactly once. Key constraints include an input array length ranging from 1 to 100, and individual string lengths also varying between 1 and 100 characters, all composed solely of lowercase English letters. These constraints guide our approach to efficiently categorize and organize the strings into their respective anagram groups. The Python code shown here tackles LeetCode problem 49, which focuses on grouping anagrams from a list of strings. It uses a default dict from the collections module for efficient organization of these anagrams based on a key characteristic, the sorted arrangement of their characters. We start by creating a default dict, where each key is a tuple made from the sorted characters of a string, and the values are lists that gather all strings sharing that key. Using a tuple is important here because tuples are immutable, allowing them to be used as keys in our dictionary. As we loop through each string in the input list, we sort the characters of the string to create this key. This sorting takes O(n) log n time, where n is the string length. We then append the original string to its corresponding list in the dictionary. Finally, the function collects all the lists of anagrams with anagrams.values and returns them. Overall, This solution efficiently groups anagrams in O n to k log k time, where n is the number of strings and k is the longest string length, providing an optimal method for solving the problem. The time complexity for grouping anagrams is O n k. Here, n represents the number of strings in our input list, while k is the maximum length of any single string. To group anagrams, we first need to iterate through each string to create a key. This key is typically generated by sorting the characters in the string, which takes OK time. After creating the key, we then insert it into a hash map, which leads to a total of n OK operations overall. Now, let's discuss space complexity. It is also ONK. This is because our hash map needs to store all n strings, and each of these keys can be up to k characters long. So the space required for both the keys and values in our hash map also adds up to O, N, or K. Understanding these complexities helps us grasp the efficiency of our solution and its limitations when dealing with larger inputs.